Hello, Hello, class. Welcome to another video for this course. In this video, we are going to talk about second derivative. Basically, we want to, in general, when you have a function, we can study the behavior of the function, for example, to see whether it's increasing or decreasing, and also we can discuss the concavity of the function. And for that, I want to show you in this section what is the relationship between those behavior of a function and their derivative, and finally introduce the second derivative. Okay, so let's start by talking about the relationship between function and its derivative. So when you have a function, suppose you have a function that is differentiable, which means that its derivative exists, because you know that not every function has a derivative at every point. But assume that you have a function, it's differentiable, and its derivative exists, which means that you can take its derivative. What is the derivative of a function? It's also a new function, right? So this is your function, the original function, and suppose this is the derivative function, which is also a function. So for example, something that we can observe is that when you have a function and let's look at the graph of the function. Suppose the graph is whatever, I don't know, something like this. So this is the graph of f of x. So as you can see, when we look at the graph of a function, we can say, for example, okay, for example, the graph is increasing from here up to here. And then it becomes decreasing from here up to this point. And then again, it becomes increasing from this point toward infinity, right? So when you have the graph, you can see that, for example, where the function is increasing, where the function is decreasing, or even if it doesn't show any pattern at all. By the way, if you want to know what is the formal definition of increasing, decreasing, when do we mean a function is increasing? In general, if you increase the, so this is x-axis, this is the y-axis. So imagine, you can either think about the definition as xy value or input-output value. So increasing is that if you increase the x value, so increasing function, when do you say a function is increasing? It's the case when if you increase the x values, then the y values get increased as well, So like here, you see. So for example, let's say you are here and then you move and you increase the x value. You see that? What happens to the y value? Here was the height, but now height jumped up to this value. So you increase the value for x variable, you will see an increase in y variable. In that case, we say the function is increasing. And what is the decreasing function? What is the decreasing function? We say that the function is increasing if the opposite happens, which means that if you increase the x values, you increase the x values, but the opposite happens. The y values decreases. So like here, look, for example, suppose your x is right here and then you increase it. you go to the right, so you are increasing the x value. What happens to the height? The original height was right here. My initially was here, but now we went down, the height went down to this point. So while we had an increase in our x values, but we had a drop, you see, we had a drop in our y value. We had the height now dropped. This is the case when we say the function is decreasing. And in this graph, for example, the green part, which is from negative infinity up to 0, the function is increasing. So in this example, the function is increasing over negative infinity up to 0. And then from here, whatever is this value, I'm going to call it x0, from x0 to infinity. So you see, it's not like the function is increasing on the entire domain. No, in this picture, the function is increasing on part of the domain, and then it's decreasing from 0 up to this, and the function is decreasing on the interval of 0 and whatever is this point. So as you can see, a function, it is possible that you have a function that is increasing or decreasing, have the same pattern, same behavior on its entire domain, but it is also possible that the function has different behaviors on different parts of the domain. Okay, so I think that makes sense for the definition of increasing, for the behavior of the function. But what is the relationship between that behavior and the derivative? If you observe that, if you look at the derivative of function at these region, for example, we know that from negative infinity to 0 over this part, the function is increasing. Look at the derivative. What do we mean by looking at derivative? Derivative at any point is the slope of tangent line. For example, look at this point. This is the tangent line, right? So my point is that if you draw the tangent line for any value, for example, draw the tangent line here, or draw the tangent line here, or draw the tangent line here. What is common here is that all of these tangent lines have a positive slope, okay? And also the same behavior here. Over here, if you draw the tangent line, or if you here draw the tangent line, all of these lines have a positive slope. So what we observe here is that if the function is increasing, then the slope of tangent line is positive. The slope of tangent line is positive as at those points. But what is the slope of tangent line? What is the slope of tangent line? It's the derivative, right? Derivative at those points is positive. So the derivative is positive. So this is the relationship between the behavior of the function and its function. If your function is increasing, if the behavior of function is that the function is increasing, then its derivative is positive. And if the function is decreasing, for example, look at this part between 0 and this x0. If you draw a tangent line, for example, here I'm going to draw a tangent line. You see, the tangent line has a negative slope. Or draw a tangent line here, or draw a tangent line here. All of them are like decreasing, so they have a negative slope. So what we observe is that when the function is decreasing, the slope of tangent line is negative. The slope of tangent line is negative. Which is what? The slope of tangent line is the derivative, right? So that means the derivative is negative. The derivative is negative. So here is the relationship between behavior of a function and the derivative. If the behavior of function is that the function is increasing, so that means the derivative at that point, at that part, is positive. If the function is decreasing over that region, the derivative is negative. So there is a relationship between sign of the derivative and the behavior of the function. So you can also see this picture. Look, in this graph, at point A, okay, point A, look at point A, we see that the function is going up, the function is increasing, and look at the tangent line. The tangent line also has a positive slope, which matches. Look at point B. In point B, the function is decreasing. The tangent line is also decreasing. The slope of tangent line is negative. So that was another example. So to summarize what we discussed, here is the formal definition of increasing, decreasing of a function. So when you have a function over an interval, it could be the entire domain or it could be part of the domain. We say the function is increasing when you increase the x value, you see that the f value, the outputs also increases. And similarly, we say that the function is decreasing when you increase the x value, but you see that the output is decreasing. So that's the formal definition of that, and also the relationship between the function and the derivative is that if the function is differentiable, then we observe that if derivative is positive, then the function is increasing. Remember, if the derivative is positive, the function is increasing. And when derivative is negative on that interval, the function is going to be decreasing. So let me summarize this somewhere here. So what is the observation? So if function is if function f is increasing if and only if the derivative is positive. F is decreasing if and only if the derivative is negative. So that's a conclusion, and it's a very useful result. Okay. Now, look, we want to study another behavior. Let me tell you that we want to study another behavior of a function, but before getting to that, just recall that when you have a differentiable function, so you can take the derivative, which means that if the function is differentiable, then the derivative exists. And then this derivative is also a function, right? For example, look at this example. For example, let's say y is x squared plus 5. Okay, what is the derivative? The derivative is 2x. Okay, now this derivative is also a function. The point is that, yes, this is the function f of x. F of x is a function. We take the derivative, but what is the result? The result is also a function, and it's a differentiable function, which means that now I can also forget about this and just look at this as a function, and again take its derivative, which is 2. So this is called second derivative, which means that we are taking the derivative of derivative, and we denote it by y double prime. So because the f prime is also a function, so if it's differentiable, it is also possible to take its derivative. Just take the derivative. So this is the derivative of this function, f prime, and we denote it by f prime, and it's called, so maybe I named a. So this is the function. This is the original function. we take the first derivative. So we take the first derivative, which means that we take the derivative of the function. Now we are taking the derivative of derivative, and this is going to be called second derivative because this is just the derivative of derivative. For example, I'm going to show you a couple of examples. For example, let's say your function is what? Let's say your function is 3x to the fifth 6x squared plus 10. Okay, take its derivative. It's gonna be 3 times 5, 15, x to the 4, and 12x. Now, this is the derivative. So this is the function, right? This is the original function. And this is the derivative. We took the derivative of the function. But just think about this. This is also a function. It is possible to take the derivative of this, which is going to be 15 times 4x cubed plus 12. And we denote it by y double prime. 15 times 4 is going to be, 15 times 2 is 30. I think it's going to be 90. So it's going to be 90x cubed plus 12. And it's called the second derivative, because we took the derivative of the first derivative. So you see, we can introduce the second derivative. Or let me show you another example. For example, sine of x, think about y equal sine of x. Okay, take the derivative of this function. It's gonna be derivative of sine is cosine of x. Now, it is possible to continue this because cosine also has a derivative. So we can take the derivative of derivative. What is the derivative of cosine? It's negative sine of x, you see? So if a function is differentiable, then you can take its derivative, then you can repeat that, take the derivative of derivative, and so on. So that's the second derivative. If you know, and you know, the computation is so easy. If you actually learned how to take the derivative, second derivative just has the same rule because you just apply the same thing to a function. But it happens to be the derivative of a derivative of another function, so it's called, it is placed in the second order. Maybe I should give you another example. For example, let's say y is natural log of x plus e to the x plus x cubed, for example. Take the derivative of this function. Derivative of natural log is 1 over x. Derivative of e to the x is e to the x, and derivative of x cubed is 3x squared. But now this new function, the derivative, is also a function. So it is possible to take the derivative of this. Derivative of 1 over x is negative 1 over x squared. This is quotient rule. So now I'm applying the quotient rule. Derivative of exponential function, and this is polynomial, 6 to x. So this is the, this is gonna be f of x, right? This is gonna be, this is the first derivative of f, and this is the second derivative, which means that we took the derivative of f. Okay, so that's it. That's second derivative. And here in your function is start by the limit definition, but that's it. Now, what is the application of second derivative? Why is it good? What part of information it gives us? Look at the function. Suppose you have the graph of the function. So we already answered the question about increasing and decreasing. We saw what is the relationship between the behavior of function in terms of increasing, decreasing, and the derivative of the function. But now look at this picture. Look at this picture. Even though a function is increasing, like these three graphs, they could increase at different speed. For example, one graph, look at these three graphs. it is possible that the graph increases fast. So there are three basic behavior that maybe one of them increases fast, more and more rapidly. One of them, like the middle one, increases at the same rate, same speed. And one of them, actually the last one, increases slowly. So there is a difference between the rates that they are increasing. How that's different behavior is connected to second derivative. And also that you can observe that even when the function is decreasing, for example, here your graphs are decreasing, but this one decreases fast, the middle one decreases at the same rate, and the last one decreases at different rate. So it could be increasing and decreasing, and they have different speed, different rate of change. So how is that connected? So it is possible to look at the, like here, look at this graph. Okay, so we see that we see the curve and we see the tangent line. And then also we see a picture on the right. So so let me first talk about concavity. At left, you have a function that is concave up, right? So a function, when the graph is like this, it is concave up. And when the function is like this, it is called concave down. Okay. So what I see is that when the concavity is up, so what happens to the tangent line? So the tangent line is decreasing, and then it's decreasing and then it gets increasing. So which means that the slope is negative, the slope of tangent line is negative, and then it changed to positive. So there is a change, or maybe I put it this way. The derivative, because tangent line, okay, maybe I write this down. Maybe I write this up, but I'm trying to explain, maybe I wrote it. So when you have this picture, what do you observe? This is concave up, right? This graph is concave up, okay? And look at the tangent line. So it's like, first is, look, it's here, and then it's here, and it gets flatter and flatter. Here is flat. So it's like it's decreasing, 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 flat, and then it changed to become increasing, 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 increasing. So what happens is that, recall that tangent line is related to the derivative. So what is the behavior of the function here? The tangent line is related to the derivative, to the first derivative. First derivative changes from decreasing, in other words, the derivative is increasing, because as you increase the x values, what was the definition of increasing? You increase the x value, the function output goes up. And here you have the case, because look here, the slope of tangent line is negative, here is negative, here is negative, here is 0, then here it's the slope is positive, here is positive but it's sharper, here is positive but it's sharper, here is positive, it's so sharp. So the change that we observe here is that as we increase the x values, the slope of tangent line increases, which means that f prime, the derivative, increases, right? So that's the observation. The graph is concave up. What's happening to the derivative? by looking at the slope of tangent line, we see that the f prime, the derivative is increases. Now, what is the relationship between being increasing? Look at this as a function, Look at this result. What is the relationship between decreasing and its derivative? If any function is increasing, then its derivative is positive. So in this case, this function is increasing, therefore its derivative, which is going to be the second derivative, right? The derivative of f prime is positive. So that's the conclusion. That's the conclusion. What is the conclusion? The conclusion is that you have concave up, therefore the second derivative is positive. Now, look at a graph that is concave down. Let's see what we can get from the picture. This is x, this is y. Suppose this is the graph. From the graph, you can see that the graph is concave down, right? Now, let's see if we can see any relationship between the derivative of the function and the concavity. So the graph is concave down. Now let's look at the tangent line. So this is a tangent as we increase the x value. So I'm starting from left. Here is the tangent line. It's positive and it's very sharp. It's big. The slope is big. Here is the tangent line. It is still positive, but it's flatter. Here is the tangent line. Here is the tangent line. So the tangent line decreases. And finally, at this point, the slope of tangent line is 0. And then it gets decreasing. You see, the tangent line is decreasing, and it becomes smaller. The slope becomes smaller and smaller. So the behavior that we observe is that as we increase x values. Why? Because I started from left, right? We start from left and we go toward right. So we are when we are doing this, we are increasing the x value. What happens to the slope of tangent line? A slope of tangent line decreases, right? Because first it's positive and it's very sharp. It's big. This is a big number. Then it becomes flatter, and finally it becomes 0, and then it becomes negative. So it decreases. So the slope of tangent line, which is f prime, the first derivative, decreases. Now, what is the relationship between decreasing? What piece of information it gives us if a function is decreasing? We just observe that if a function is decreasing, then its derivative, its first derivative is negative. So its derivative, whatever is this function, its derivative is negative. So this function is the first derivative, but its derivative, which means that I have to take another derivative from this function. The second derivative is negative. Okay, so here is the final conclusion. You see a concave down graph. You conclude that the second derivative is negative. And here is the big picture. Okay, so we have these two conclusions. You have, by the way, what is concave down? F, okay, f, function f, y equal f of x. The f, the original function is concave up, then its second derivative is positive. The original function is concave down, the second derivative is negative. So far we got 3 results. Two results, sorry. I'm gonna put a summary of the result we observed so far. Okay, first, if function f is increasing, then the first derivative is positive. if it's decreasing, the first derivative is negative. If it's concave up, the second derivative is positive. And finally, if the function is concave down, the second derivative is negative. So this is the main result of this section, and you need to apply them. So in practice, you're gonna apply the results. So just pay attention that this is first derivative. This is using about first derivative, and this result includes second derivative. So by knowing the sign of first derivative and second derivative, we can get information about the behavior of the graph of the function. Okay, so that's it. That's the main goal of this section. By the way, here is the formal definition, and yeah, here is the formal definition of concavity. Concave up, concave down. Yes, it's concave down. Sorry, it's concave up if f prime is increasing, which means that its derivative, the second derivative, is positive. Function f is concave down if the derivative is decreasing, which implies that the second derivative is negative. So I recommend you to practice these activities. They are good warm-up practices. But that's it. That's all that we need. The main conclusion is this. And in terms of computation, you just, if any question asks you to compute a second derivative, right, just apply the same rule as you already know. For example, if a function is given, like let's say f of x, let's say they give you f of x as, I don't know, anything, for example, sine of x plus cosine of x, something like this. And so, you know, this is a function that is differentiable. You can compute the first derivative, which is the derivative of sine is cosine, derivative of cosine is negative sine. But because this is also a function, you can apply the same derivative rules, the rules that you already know, to compute the second derivative, which means that you should take this is the derivative of this function. So take the derivative of cosine, which is negative sine. Now, negative takes the derivative of sine, which is cosine of x. Then you end up by a new function. And you can repeat this process. So you can take derivative at any degree that you want, at any level that you want. And you can, as long as the function is differentiable, by same rule. My point is this rule doesn't change. It's just at every step, remember that this is a function. Now, what rules do I know about taking the derivative? Apply the same rule to compute the second derivative. Before ending this video, I just wanted to show you a couple of these exercises. These are fun exercises, and it helps you to better grasp the idea of this section. For example, this graph is given, and this is the graph of f of x. The question is compare f prime, and f double prime, which means that the value of the function, its derivative, and its second derivative. For example, at point 3, okay, at point 3, the function is it positive or negative? It's positive. The value of the function at 3 is positive. What about the derivative at 3? Okay, the derivative at 3 is the slope of tangent line. If this is the tangent line, so it's increasing, so the slope is positive. But what about the second derivative? Second derivative goes back to concavity, right? And at 3, the function is concave down. So that means the second derivative is negative, okay? And then you can check your answer, okay? So by looking at the graph, I determined the first one. By looking at the tangent line, I determined the second one. And by looking at the concavity, I determine the last one. And you can repeat that here. For example, point A. We need to determine the sign for f prime, and f double prime. Point A, where is A? A is right here. Okay, at A, the function cross x-axis, so it's 0. See, at A, the function is 0. What about the derivative? At A, the function is decreasing, you see? So the slope of tangent line is negative. So the first derivative is negative. Now, to determine the second derivative, it's all about concavity. At A, the function is concave up, right? It's concave up, so it's gonna be positive. Okay, maybe I do B as well. So at B, the function is negative. The value of the function, the output is negative. The derivative, actually at that point, the tangent line is flat. If you draw a tangent line at B, you see that the tangent line is parallel to horizontal axis. It's flat, so the slope is 0. And second derivative, concavity. Function is concave up, so this is going to be positive. Part C. Part C, okay, it's cross x-axis, so f is 0. The function is increasing, so the first derivative is positive. And second derivative, concavity. Again, it's concave up, so the function, the second derivative is positive. Now D. The value of the function at D is positive. The height is positive. But for f prime, we look at the tangent line. Okay, tangent line is horizontal at that point, so the slope, it has a slope of 0. And in terms of for the second derivative, it relates to concavity. The function is concave down, so now the second derivative is gonna be negative. And finally, at E, function is positive. Okay, it's decreasing, you see? At E, the function is decreasing. The slope of tangent line is negative. And in terms of concavity, it's concave down, so this is also negative. Yeah, okay? So I encourage you guys to play with these exercises. Try to do the activities, play, especially these one that have a graph, like this one, you see? And try to play with them. It's more like a warm-up. But in general, that's the takeaway from this lesson, that, okay, there is a relationship between the behavior of the function and its derivative. You can if the function is increasing, decreasing, you can tell about the sign of the first derivative. And if the function is concave up or concave down, then you can talk about the sign of the second derivative. And if your question is that how to calculate the second derivative, just apply the same rule that you learned for first derivative. Just take so you have an original function, you take its derivative. Now its derivative is a new function, right? So it's possible to compute its derivative. Just take another derivative. That's gonna be the second derivative. And to do that, you just apply the same derivative rule as always. That's all about this section, and now you are ready to do the exercises for this section. Thank you for watching this video. I'll see you in the next one.